Dear friends, today I want to discuss with you about pulse amplitude modulation. Now, before going to discuss what is pulse amplitude modulation, you must have some idea about what is pulse. So, I am giving you two very simple examples. You are familiar with such kind of phenomena. So, just go through these examples. You are all familiar with lightning and you are very fond of such kind of things. Okay, so I hope you got an idea about what is pulse. Now I am not going to debate with you that whether the above two examples what I have given you just earlier, that whether these are impulse or pulse. I am just want to give you an essence of what is pulse or say impulse. Now the question is, so what is pulse? Pulse is a tremendous amount of energy within a fraction of second, say instantaneously, rather say instantaneous. Now I want to mathematically formulate what is impulse and what is pulse. Fine. So first, as you can see from the first figure, as you can see from this figure, that I have shown here a sequence of pulses, and I will just mathematically formulate these expressions, this sequence of pulse. And in the second figure, I have shown you a sequence of pulse. So this is the impulses and a sequence of impulse, and this is a sequence of pulse. Now I want to formulate first this sequence of impulse. Before going to define mathematically impulse, I have to know what is Dirac delta function. Now you all know that delta function is represented by delta t. This is equals to 0 except t equals to 0. As from the figure you can see, except t is equals to 0, for the first function this is equals to 0, and for t is equals to 0 it has a value I. Actually theoretically I can say that the area under the curve, say minus infinity to plus infinity, this is the ideal definition of Dirac delta function, delta t into dt, that is equals to 1. Fine. Now here we have considered that the strength of the impulse function, strength of the impulse function, strength of the impulse function is I. That is the area, that is the area under the curve is I. Fine. So the area under the curve is I. Actually, so when t is equals to 0, the strength of this impulse will be I. Now, if we want to express it in terms of function, this pulse, if we want to express this impulse mathematically with the help of our Dirac delta function, we can define it as v function of t is equals to I summation over k equals to minus infinity to plus infinity delta into t minus k t0. You can see very easily from this function. So this pulse is propagating along the positive t direction. So the equation is t minus k t0. If I place k is equals to 1, then we will get the second pulse. If I place k is equals to 2, then we will get the next pulse, and so on. Fine. So now this pulse, this impulse, what is the duration of this impulse? So this is instantaneous. Now we want to define pulse. Clear? So what is the difference between pulse and impulse? Actually, pulse have some finite duration. You can see from this figure. You can see from this figure, this the width of this impulse is very instantaneous. That is, it has no width actually. Theoretically, it has no width. But in our second figure, you can easily see that the width of this pulse is tau. It extends from minus tau by 2 to plus tau by 2. So the difference between pulse and impulse is that pulse have some finite duration, whether impulse is instantaneous, that is, it has no time scale, that is no width. Okay. So I want to define now pulse in terms of Fourier expansion. So pulse can be written as Vt equals to A0 by 2 plus summation over n is equals to 1 to infinity an cos 2 pi n t by t0. Fine. Now we are considering only cosine term because from the figure you can see that it is an even function. Fine. Now you are familiar, don't get confused, you are familiar with Fourier expansion in terms of x. So you are writing actually Fourier expansion as a0 by 2 plus summation over n is equals to 1 to infinity an cos nx. Fine. You are familiar with these terms. Okay, now just we have replaced here as x equivalent to theta and theta is equals to omega into t. So this is equals to 2 pi by t0 into t. Fine. So we have replaced x by 2 pi t by t0. We have considered here that the variable is t and the time period of this pulse as t0. Fine. So I can write this pulse as v function of t, that is equals to say a0, capital A0 is equals to small a0 by 2 plus summation over n equals to 1 to infinity capital An cos 2 pi nt by t0. Fine. So this is the expression of pulse. So what are the values of a0 and an? We all know from the Fourier expansion that I just want to remember this expansion as a0 is equals to 1 by t0 integration minus tau by 2 to plus tau by 2 v function of t into dt and an is equals to 2 by t0. You just replace the functions in terms of time scale. Okay, minus tau by 2 to plus tau by 2 v function of t cos 2 pi n t by t0 into dt. Fine. This expression is in the time scale. Okay, and you can see that this extends from minus tau by 2 to plus tau by 2. Okay, these pulse present from in time scale from minus tau by 2 to plus tau by 2. So we are integrating from minus tau by 2 to plus tau by 2. And the strength of this impulse is I. So actually I am writing it in terms of the Dirac delta function as capital I into summation over k equals to minus infinity to plus infinity delta t minus k t0. Okay, t minus k t0. So that is equals to, from our above Fourier expansion, I can write it as I by t0. Okay, I by t0 plus 2I by t0 into summation n is equals to 1 to infinity cos 2 pi nt by t0. Okay, so I have defined mathematically what is pulse. I have defined mathematically what is pulse. Now I want to discuss with you, I want to give an idea about pulse amplitude modulation. Now pulse amplitude modulation comes under the common name pulse modulation, and pulse amplitude modulation is the most famous. There are various kind of pulse modulation like pulse position modulation, pulse time modulation, frequency modulation, etc. So we are going to discuss with you here the pulse amplitude modulation. Okay. Now, as the name implies pulse amplitude modulation. Okay, this is called PAM. So, as the name implies, we are modulating the amplitude of the pulse. We are modulating the amplitude of the pulse in accordance with the modulating information signal m function of t. Fine. So this is called pulse amplitude modulation. Now we can in principle, that is theoretically, we can get a pulse amplitude modulated wave very easily. Say this is a multiplexer. Okay, say this is a multiplexer, and we are applying here the information signal, and here we are applying the pulse wave. This is the pulse wave and this is the information. Okay, so here we will get the pulse amplitude modulated wave. Okay, now actually the multiplexer, as a multiplexer we can use a balanced modulator. We can use a balanced modulator as multiplexer. Fine. So we can use a balanced modulator as multiplexer. Now, what will be the expression of these pulse amplitude modulated wave, or how we can get it? We have just shown you in principle what would be the figure, what would be the expression. Now I want to draw it. Graphically. Fine. So for that purpose, I am considering a very simple information signal. Say this is our information signal. Okay, and now this is the pulse. Fine, this is the pulse. So here, instead of considering the strength of the pulse as I, we are considering the strength of the pulse as unity. Fine. So this is the pulse and the strength of the pulse is unity. Okay. So and also the and also the and also the time period of the pulse is Ts instead of T0, what we have considered earlier, and this is dt. Fine. Dt is the width of the pulse, what we have earlier considered as tau. Okay. Now this is a multiplexer. This is a multiplexer. Okay, and we are applying here these two signals. This is VPT, and here we are applying, say, this signal, information signal, and now we are getting ET, that is equals to VPT into MT. Okay, so here the area of the pulse, is 1. So in our previous expansion, in our previous expression, we have considered here I. You can remember that. In our previous expression, you are considering here I. Now I will replace I by 1 and I will replace T0 by Ts. Fine. So what would be the expression of Vpt in our case? So Vpt is equals to dt by Ts. So area, so height of the pulse is 1 and the width of the pulse is dt. So height is equals to 1, area, and width is equals to, and width is equals to and width is equals to dt. So area is equals to 1 into dt. So this is the strength of the pulse. The strength of the pulse is 1 into dt. So instead of I will write it here dt by ts plus 2 dt by ts 2 dt by ts, okay, into cos 2 pi t by ts. This is the first term. I am expanding it, plus cos 2 into 2 pi t by ts plus etc. Fine. So I am just multiplying it with mt. The modulated wave will be Vp into mt. So what would be the modulated wave? Et is equals to Vp function of t into m function of t, that is equals to dt by ts into mt, fine, plus 2 dt by ts into m function of t into cos 2 pi t by ts, etc. Okay, so what would be the form of et? What would be the graphical form of et? You can just guess it. So this was our say modulated signal. Okay, this is the envelope of the modulated signal, fine, and the pulse, the amplitude of the pulses are get modified in accordance with the envelope of the signal, fine. So this is the actually modulated wave, fine. Now the form of the pulse amplitude modulated will be this: the pulse amplitude modulated wave, fine. This is the pulse amplitude modulated wave. Actually this is also called natural PAM. This is also called natural PAM. Why? Because the top of the pulse is following the envelope of the information signal, that is mt. Actual envelope of the information signal is being followed by the pulse, so this is called mt. If the top of the pulse is flat, so this is called flat top sampling. Okay, so I am not going to discuss it here. So this is the actually amplitude modulated wave, fine. Now from the expression of amplitude modulated wave, you can see just, so I am just writing it, the modulated wave again. So dt by ts into mt plus what would be the expression of the modulated wave? Plus 2 into dt by ts into mt into cos 2 pi t by ts plus dot dot. Fine. So I want to show you here, this is a scalar term. This is a scalar term. Clear? dt by ts. So dt is very less than ts. So this is always less than 1. Fine. So since this is always less than 1, so actually the amplitude of the modulating signal get decreased, get reduced. Clear? So from this we can see that the amplitude of the information get reduced. This is one of the problem in case of PAM. Okay, and now if we minutely observe this expression, clear? Now I can say, for example, mt is of the form cos omega mt. Okay, whatever may be the amplitude of the mt, I am just not considering here. And cos 2 pi t by ts, if I consider that this is the angular frequency is omega s, so I can write it as cos omega st. Now I am multiplying it, so I will get two terms. So I will get two terms. One is cos omega s plus omega m into t, and the other will be cos omega s minus omega m into t. There will be several other terms. So what kind of modulation it is? So it is like DSB-SC. Fine, and there are infinite number of DSB-SC terms. Infinite number of sorry, there will be infinite number of DSB-SC terms. Okay, there will be infinite number of DSB-SC terms. So to transmit, to transmit, we need a wide bandwidth, a wide bandwidth transmission system. Fine. So these are the two drawbacks. These are the two drawbacks of pulse amplitude modulated system. So the amplitude of the information get reduced here. This is the first problem, and the second problem is that to transmit it, we need a wide bandwidth transmission system. Fine. So you can ask then, what is the benefit? What is the advantage? What is the advantage of using PAM? Fine. What is the advantage of using PAM? Why we will use PAM? It will be clear. I am just showing you. A graph. Then it will be clear to you. Okay. So this is the time scale. Fine. This is the time scale, and I am considering a signal M1T. Fine. I am considering a signal M1T. Okay. This is the pulse being modulated in accordance with this signal. Fine. The pulse being modulated in accordance with this signal in time scale. Okay, this is M1 function of t. Fine. Now say another signal is here, M2. Okay, say another signal is here. Another signal is here. Say this is M2 function of t. Okay. Now I am using the same pulse train. I am using the same pulse train with these pulses. What you can see from these two, from this graph, clear? What you can see? You can see that the pulse modulation allows pulses carrying different modulating signal to be interleaved in time. Fine. I can say that pulse modulation, I can say that pulse modulation allows us uh, to be allows us carrying different modulating signals. I have shown here M1T and M2T, different modulating signals to be interleaved in time. Okay, to be interleaved in time. This is called time division multiplex. Time division multiplexed. Okay, fine. This is called time division multiplex. Remember, in the same time scale, see from the here, in the same time scale, we are accommodating two signals, M1T and M2T. These pulses are not interfering each other. Fine. So this is the benefit. This is the benefit of using a pulse amplitude modulation technique. So how we can achieve this in practice? How we can achieve this in practice? A simple manner. In a very simple manner, we can achieve this. Just to this, we use a synchronous analog selector switch using synchronous analog selector switch we can realize it we can realize sorry we can realize it. Just see this example, just see this figure, sorry, just see this figure. Okay, now we are using to switch. Say this is first position, this is second position, this is third position, etc. Okay, and this is the communication channel, and here is another switch. So this is 1, this is 2, this is 3. So I am applying here m1 function of t. Okay, I am applying here m2t. I am applying here m2t, etc. Fine, and this is the selector switch, and from here through a filter I am just getting m1 function of t, and again through a filter I am getting m2 function of t, m2 function of t, etc. Fine. The this is called commutator. You are familiar with this term, and this is called decommutator. Okay, this is called decommutator section. Clear? These circuits act to synchronously connect the transmission line output. This is the transmission line output to each separate channel demodulator in the same sequence of the multiplexed. Okay, so when we are touching this switch to one, and this communication channel is get active for M1T, and we can receive by touching the decommutator switch to one port and filtering out M1T. So here the multiplexing of several PMM signal is possible From this simple diagram and from our previous discussion, you can conclude that the multiplexing of several PM signals is possible because the various signals are kept distinct and are separately recoverable by virtue of the fact that they are sampled at different times. You can see from here, they are sampled at different times. In time scale, M1T is sampled here and M2T is sampled here. So these are sampled at different times. Fine. So this system, and that's why I called it. We know that it is called an example of TDM, that is time division multiplexing. Okay. So now I can just these time division multiplex signal, these time division multiplex signal, I can just transmit it. I can just transmit it. We can transmit it. We can transmit it through the channel. Okay, through the channel. So for these PAM-AM, we can use amplitude modulation. These PAM signal, I can transmit it through amplitude modulation or through frequency modulation through the channel. Fine. So when we transmit these PAM signal through amplitude modulation, this is called PAM. When we transmit these pulse amplitude modulated signal by frequency modulation, then this is called PAM-FM. Fine. Now, what are the uses where we use this PAM-AM or PAM-FM? Where we use this pulse amplitude modulation scheme? Actually, you can see, I already discussed that there is a bandwidth problem. We need wide bandwidth transmission channel, and as well as the signal, the amplitude of the baseband signal, that is the informant signal, get reduced by the factor dt by ts. But now it is widely used. Actually, it is widely used in, it is used, sorry, actually it is used in instrumentation system, instrumentation system, and it is used in HD converter used for computer interfacing. Fine. So the uses of PAM, I have give you two examples where we use PAM. Okay. So I hope that you have enjoyed this class and you got an idea about what is pulse amplitude modulation, what are the disadvantage, what is the advantage of pulse amplitude modulation, and where we use and what are the applications of pulse amplitude modulation. Fine. Thank you.